Hello students, welcome to the third lesson in this chapter where we have been studying the graphs of trigonometric functions. In the first two lessons, we have covered extensively the graphs of sine and cosine functions and their generalizations, and we also discussed general properties of graphs and trigonometric graphs of trigonometric functions particularly. Okay, the concepts of phase shift, the concept of raising the mean position, and the concept of the amplitude. All these ideas have been discussed. In this lesson, we will look at the graphs of secant and cosecant functions. Okay, so we begin. Secant. The technique we will use here in graphing will be to consider the reciprocal definition of secant, which is sec x is 1 over cos x, right? Now, let us create a table of values of angles and their secant values. We begin with the quadrantal angles as we did with sine and cosine, and then we will see if we need more information to come up with a graphical outline of the function. Okay, so first I will go with quadrantal angles. That would be 0, pi over 2 going anticlockwise, pi, 3 pi over 2, and 2 pi. Okay, and what are the values? Cos 0. Now remember the definition of cosine, cos x, that is cos x is the x coordinate, right? And we can also keep the unit circle in our mind, or just have a rough diagram in front of you. At 0 radians, the x coordinate is 1, okay, on the unit circle. So cos 0 is 1, therefore its reciprocal sec 0 is also 1. Reciprocal of 1 is 1. At pi over 2, 90 degrees, we are on the y-axis. The point on the y-axis is 0, 1. So the x coordinate is 0 now. Cos pi over 2 is 0. When it is 0, its reciprocal will be undefined. But when it is undefined, we are going to not just be satisfied with that. It is either going to be infinity, tending to infinity, or to negative infinity, or maybe to infinity on one side of the asymptote and negative infinity on the other side of the asymptote. We will see that. Okay, when we start graphing, we will consider which infinity it is going to, plus or minus. Then back to x-axis again at pi, negative x-axis. The x coordinate is now -1, right here. So when the x coordinate is -1, cos x is now -1, so its reciprocal also will be -1. And 3 pi over 2, we are again on y-axis. The point on the unit circle is 0, -1. So the x coordinate is 0. Cos 3 pi over 2 is 0. Hence, sec 3 pi over 2 is again undefined. What that means is plus or minus infinity on two sides. And finally, 2 pi is the same as 0, right? Its value is 1 again. let us see. We try to first plot these values in the graph, and we will try to then develop an idea. Okay, we will see what more angles we will need. Go to the graph and start plotting. So at 0, so here is the graph, and so from 0 to 2 pi we will be looking at the right hand side, the right hand part of this graph. 0 here, 2 pi there, so halfway mark is pi. Here you have pi over 2, and here 3 pi over 2. Okay, and our values now from the table. Okay, I remember, and I'm going to plot them here. Sec 0 is 1. Sec pi over 2 is undefined. Okay, that's because it's 1 over 0. So I said that, the meaning of undefined now is not something that we don't know. The meaning of undefined is it's going to go to infinity. So I'm going to, for now, draw this asymptote at that point. And then you move, maybe I need to choose a different color for the asymptote. Okay, and then you move on to the angle pi, and at pi we said the value is -1. Okay, and at 3 pi over 2 again you have an asymptote. Okay, and at 2 pi you are back to 1. Okay, now we are trying to think of a function which hits 1 and -1 like this and is going to infinity near those asymptotes. Now what is not clear to us is in what direction it is going to infinity, right? For that, we will try to get help by evaluating maybe some more angles. Okay, so let us do that. At, let's say, between 0 and pi over 2. Now if you zoom in here in the between 0 and pi over 2, you can consider, say, pi over 4, right? That's 45 degree. Cos pi over 4. Now you have to remember on the unit circle. Okay, cos pi over 4 is the x coordinate, which is 1 over root 2 over 2, or 1 over root 2. Okay, before it is rationalized. So it's reciprocal. Sec pi over 4 is going to be root 2. Now what's the value of root 2? Approximately it is 1.4142. Okay, irrational number, infinite decimals, but those are the first four. 1.4142. So that value is going to be somewhere in the, by the way, pi over 4 is in the middle here, midway between 0 and pi over 2, and its value is 1.4142, so a little less than 1.5, let's say, somewhere there, right? So what would be a safe way to sketch a graph here? It's at starting at 1 and then going to infinity when it is close to pi over 2. It makes sense that we draw our graph like that, right? And not only that, we have this value at pi over 4, which is under root 2, and then based on that we can draw like that. But also we can remember this is the first quadrant. In the first quadrant, every trigonometric ratio is positive, so secant is also positive. And so if it is going to infinity in this quadrant, it is going to go to positive infinity. This is from the left side, okay, when the values are less than 90 degree. So we are in the first quadrant. Now on the next quadrant, what happens when you are on the right side of this asymptote? So you are greater than 90 degree, at 90.0001 degree. Again, we will do both the things. We will use the analysis of the sign in the second quadrant, but also we can look at least one specific value. Okay, consider 3 pi over 4, which is between 90 and 180, right? 135 degree. And going to the unit circle, it is an opportunity for us to review some of these ideas of what you call the unit circle. Okay, so I'm going back there, the techniques of unit circle, and the techniques of evaluating the trigonometric functions, the values of trigonometric functions at different angles. So your 3 pi over 4 is here, 135 degree. Okay, you are in the second quadrant. Its reference angle will be the same as will be pi over 4, for which we just wrote the value. And as you can see in the diagram that I drew also here, the x coordinate is now negative, but the same length, right? There are two similar situations, the same reference angle as pi over 4, but on the negative side. So the x coordinate is negative, and it doesn't take much time to realize the value of sec 3 pi over 4 is going to be negative root 2. Okay, that means when I now look at the graph here, I'm going to again zoom in between pi over 2 and pi now, and I'm at 3 pi over 4. Okay, and the value is negative root 2, which is negative 1.4142. So maybe approximately there somewhere. Okay, and that is, now you think of moving from 180 to 90. Okay, let's move from right to left. At 180, the value is negative 1. And when you come down to 135, you are at negative 1.4142. And then close to 90 degree, you are going to an infinity because it was 1 over 0. Okay, which infinity now? It would make sense because these are continuous stuff in this region, it would make sense to predict that this should be the graph. Okay, so you see this, the asymptote is at pi over 2. On the left side in the first quadrant, it goes to plus infinity. On the right of it in the second quadrant, it goes to negative infinity, because secant, like cosine, is positive in the first quadrant, negative in the second quadrant. Okay, and you can complete the rest of the table with other values, but now when I give you the rest of the diagram, I'm sure you'll see it. Okay, beyond 180 degree, now when you move towards 3 pi over 2, between pi and 3 pi over 2, here you are in the third quadrant. In third quadrant also, your x coordinate is negative, right? So cosine is negative, hence secant is negative, hence you will be still going to more negative values. So from here it will go like that, and when you are close to Okay, that doesn't look pretty like a line. So let me try to continue as a line like that. Okay, so it will be again asymptotic to that line there, but towards negative infinity. And then when you are in the fourth quadrant between 3 pi over 2 and 2 pi, okay, when you are in the fourth quadrant, x coordinate is again positive, right? So the secant will be positive. So you'll see that your graph again looks like this. You're asymptotic to positive infinity and gradually it comes down and meets 1 there. Okay. This is the graph of secant on its fundamental period, you can say, between 0 and 2 pi. But now, for the sake of completion, let us try to extend it. You can see clearly what happens here. It is going to be like that. And similarly, if you go to negative angles, like between 0 and negative pi over 2, after all, negative pi over 2 is what? You are going now clockwise. So you are in the fourth quadrant and the values will be positive. And as a result, you can see your graph has to be like that, asymptotic there and gradually coming down like that. So this is a typical graph of secant function. Okay. Um, there are many things remarkable here, and we have already talked about. One more thing I will point out, and you have already seen, is this. Look at this line and this line. Okay, so the two green dashed lines that I drew just now, their equations can be written. I'm going to write on the left side here, okay, as y equals 1 and y equals -1. And you can see that the values of secant are either less than -1 or more than 1. You don't see anything between -1 and 1. Okay, they can be equal to 1 or -1 at like 0 or pi, but not less than 1 or greater than -1. And that is again, if you think analytically also, you can understand that, because secant is reciprocal of cosine, right? Cosine takes values between -1 and 1. So secant can only take values either less than 1, because you are doing the reciprocal. 1 over values less than 1, that will be more than 1. That is the reason you see graphs like this. And sine and cosine take values 0 at different angles, right? Because of that, all other ratios which are either reciprocals or have sine or cosine in the denominator, in some formula, will have these asymptotes. They will take values tending to infinity um, at different angles. Okay. So you saw how it happens with secant. And this is a blueprint, what I just discussed here, the last 19 minutes, is how you can draw the graphs of all other functions also. Okay, let us now finalize our discussion here by writing the domain, range, period, and asymptotes for this graph. The domain is where the function takes finite values. Okay, and as you can see, there are periodic intervals where you have infinite values, right? And in the graph you see that is occurring at pi over 2 and 3 pi over 2, and on the left side you can see it is at -pi over 2. So you see a pattern there, right? And the pattern, it you think, and you're thinking correctly, that it is the odd multiples, like 1 pi over 2 and then 3 pi over 2. And you can see actually after 2 pi, the next time you have an asymptote is 5 pi over, and so on. So the domain will include all x, okay, except the x which are not odd multiples of pi over 2. That is the way to write the domain. Okay, so you are basically saying domain can be any x. Writing like that means any real number x, except such that, okay, that particular line, such that x should not be like any odd multiple. So an odd number is generally denoted by 2n plus 1. 2n will always be even, plus 1 will always make it odd, right? And when you make when n is chosen as integers, you get all these different odd numbers times pi over 2. That will be the domain. And for the range, I discussed that you get everything except the values between those two horizontal lines. So when you express that in interval, you say it takes all values from negative infinity up to 1 and including 1, and then it takes, sorry, negative 1, and then it takes all values starting at 1, including 1, and up to infinity. Negative infinity to negative 1, union with 1 to infinity. Okay. And periodicity, it is dependent on cosine, right? The period of cosine is 2 pi. So the period of secant is also 2 pi. That is one way of thinking about it. But also look at the graph. When do you see the same upward U occurring again? It will happen after an interval of length 2 pi. Okay. So specifically, for example, I will now highlight in a different color. When you are at 0 here and then you are rising to plus infinity as you go to 90-degree, the exact same shape of the graph occurs not after 90, not after 180-degree, not after 3 pi over 2, but after 2 pi here, right? So from this left, that rising blue to right side left, again rising blue, you have that interval of length 2 pi. So the periodicity is not just the values, it's also about the pattern of the function, right? The whole structure of the graph. Okay. So the period is 2 pi. And vertical asymptotes, we already have answer. The vertical asymptotes are the values, are the lines, are the vertical lines where the function is not defined, right? And we mentioned that while mentioning the domain. So now the vertical asymptotes can be written as the equations x equal to those values. 2n plus 1 pi over 2, n is any integer. You can write this n is any integer for the domain also. Okay. We understand it, so I didn't write then. Okay. That is the graph of secant function, the basic graph. Now let us look at transformations, just like we looked at transformations of sine and cosine. But now these are things that go to infinity. So, you have to adjust your calculations accordingly. So for example, if you take this function sec 3x plus pi over 3 plus 1, let us see. Okay, we have to understand what that transformation does to the graph, and then we will be able to talk about the domain and range. I'm going to show you here the process. Okay, now for a general secant and cosecant function, how to calculate how to obtain the domain and range. Sec 3x plus, I have to factor out the 3. Okay, pi over 9. Remember the general sine and cosine function, that's how we factor out the b. That's like the number b, okay, in the general sine function. And then in the parenthesis, it has to be pi over 9, right? To adjust to that 3 that has been factored out. And you have a plus 1 separately. So what this will do now is, in the domain, okay, let's first discuss the domain. What was the idea of the domain? That x cannot be odd multiples of pi over 2. That was the condition, right? Which here is this. This is like your x now, the input to the secant function. So you will say to find the domain. Okay, the condition you will put is 3 times x plus pi over 9 is not equal to 2n plus 1 times pi over. Okay, so it's not x, we should not get fixated with x. We have to understand the x there was the input to the secant function, what we call the word argument. Okay, an input to a function is called an argument. So the argument of secant should not be equal to 2n plus 1 pi over. Here the argument is 3 times x plus pi over 9, so that. And then we need to solve that inequation. Okay, this is called an, in case you did not know, this is not an equation, right? This is an inequation. And it can be solved just like an equation. The same rules apply. Okay. And let us do that solving now. So what does it give you? You have to isolate x on the left side. So I'm going to divide by 3 both sides. So you get x plus pi over 9 is not equal to 2n plus 1 pi over 6. Okay, I divided by 3 on both sides. So you have pi over 6 now there. And that gives you x is not equal to 2n plus 1 pi over 6 minus pi over 9. Okay, and we have to simplify that last bit there. And when you to simplify that, I have to distribute 2n times pi over 6 will be n pi over 3. 2 and 6 will cancel, and then it will be plus pi over 6 minus pi over 9. Okay, take the common denominator of 6 and 9, which will be 18, and then 3 minus 2. So I'm doing some mental calculation here. You can do it separately. Okay, plus pi over 18 will be the result. So your domain here is x such that x is not equal to this. All right. And you can again actually now factor out pi over 3 and rewrite it as 6n plus 1 pi over 3. Okay, so it turned out to be lengthier than the spot provided there. I'm continuing down here, okay, and writing the answer. So the domain, I will finally write here, of that function is x such that, hope you can see it, x such that x is not equal to 6n plus 1 pi over 3. Now, if you need more time to understand these calculations, please do that. Okay, spend time trying to understand the calculations or meet me. Okay, I'll be more than happy to help you. That's the domain. What's the range? The range, now remember, for the range for sec x is more than 1 or more than 1, less than -1 or less than that. And how is that affected here now? You did not multiply the secant with anything. Okay, there is no coefficient for secant, so that way the range did not get affected. You know that 3x plus pi over 3 changes the inputs, but overall it will produce the same output. But you added one that will lift the whole graph 1 unit up, right? So now your range will be this. I'm wondering where can I write it? I'm going to write it on the bottom left here. Okay, let's see. Range is going to be, nothing happens on the negative side, but now you can go up to 0. Compare that with the range of the secant. Okay, from -infinity to -1. Now you say -infinity to 0 because of +1. Union with, instead of 1 to infinity, now it will be 2 to infinity. See, the infinity does not change, by adding or subtracting 1, but the finite endpoints will change. -1 becomes 0, 1 becomes 2. Okay? Very interesting question. Next, determine the period of the function 3 sec 4x. Thank God, that's relatively easy. The period doesn't get affected by 3. It changes the range actually. Okay? But 4x does, right? And what's the logic? Simple answer is the period will be 2 pi divided by whatever coefficient x has. Okay, here the coefficient of x is 4, so you divide by 4 pi over 2, that's the period. Okay, we have done that concept before, so I don't think I need to explain that more. Graph of cosecant. You have seen me go through the drill with secant in detail. So what I will ask you to do now is, you do it. Okay, draw the graph of cosecant by following the method that I did. It will be a very good exercise for you and a very good skill developing opportunity. Okay, to do some analytic work and to do some graphical skills. Sketch the graph and then check with my graph. I will pause the video and directly show you the final graph. Okay, instead of taking another 20 minutes of your time. All right. You can check your work now. The definition of cosec x we used here is the reciprocal of sin x. And here are some standard angles at which we have obtained its values. And the graph should look like this. Okay. The asymptotes are at 0, pi, and 2 pi, and so on. -pi, -2 pi on the left side. And you see the similarity between secant and cosecant. Okay, you can see them on the left and right side of your screen. This is something very similar to the graph of sine and cosine, right? If you noticed there also, if you move the graph of sine by 90 degrees left or right, you get the graph of cosine. We say the phase difference between sine and cosine, the horizontal shifting, is pi over 2, the 90 degree. and these are reciprocals. So you see exactly the same thing here. If you were to move the graph of either of these by 90 degree to left or right, you will get the other one. Okay, and no surprise there. And I wanted to go over the domain and range with you. Okay, if you have already written, you can check now. In domain, just like we avoided the odd multiples of pi over 2 earlier, now it will be even multiples of pi over 2, but the even multiple of pi over 2 would be just the multiple of pi, right? The 2 gets cancelled. And you can see that at 0, pi, 2 pi, and on the left at minus pi, there are asymptotes. So your domain is going to be all x such that x is not a multiple of pi. Okay, n is any integer. Okay, and the range of the function is all values that are not between -1 and 1. So that part is the same. And the period is still 2 pi. The period of the same as that of sine x. No? And the vertical asymptotes would be exactly where you the values which are not in the domain, sorry, equal to now. The equation should be x equals n pi. Okay, for any integer n. Let us look at some practice problems on this graph of cosecant. Find the exact value of cosec pi over 6. This is a simple practice in, again, reviewing the unit circle technique. And cosec pi over 6 is reciprocal of sine, so 1 over sine pi over 6, and sine pi over 6 is the y coordinate, right? By definition, sine is y coordinate corresponding to angle pi over 6, where the coordinates on the circle are root 3 over 2 and 1 over 2, right? The y coordinate there. So that's going to be 1 over 1 over 2, which is 2. Okay. Next, find the value of sec 1.58 to the nearest tenth. Okay. And the reason I wanted to include this here is to talk to you about how to use the calculator. Of course, we are not going to do this by hand. 1.58 is not a standard angle. You use a calculator. Some calculators will have the sec button in it. Okay. But most do not. They will have sine, cosine, and tan only. So what you should do is evaluate the sec 1.58 as 1 over cos 1.58. Okay. And remember, if the unit is not mentioned like this here, that is radians. So make sure your calculator is in radians mode and evaluate that. I will also do so and write the value here, and you can check if you are especially using the radian mode correctly and if you are rounding to the nearest tenth correctly. And the answer is negative 108.7 when you round up to nearest tenth. Okay, it's 108.653, so that becomes 108.7 approximately. And if you wondered, that's a large value for a trigonometric function to have. It's not surprising because remember, secants can go to infinity or negative infinity. Here it is negative 108. And that large value is because, if you think about it, 1.58 is close to 1.57. Okay, 1.57 is almost pi over 2. So we are close to the 90 degree here. a little more than 1 point. Now that it's negative here because it's in the second quadrant. 1.57 is like pi over 2, 90 degree. So this would be a little more than 90 degree, right? And remember the graph of secant. If you go to the graph of secant, if you are a little bit more than 90 degree, I'll use a pointer here. You are in this territory, okay? And over there, the values of the function are moving to negative infinity, right? So it is negative 108.7. Okay. Next, the question is true false. The graphs of y equals 2 cosec x and y equals 1 over 2 sin x are identical. Okay. And it sounds true at the first go because cosec is reciprocal of sine, right? And 2 is reciprocal of 1 over 2. But that's not the point. 1 over 2 sin x, if you simplify, only the sin x will become 1 over sin x becomes cosec x in the numerator. The 2 stays there. Okay. So they're not the same. One is 2 cosec x, the other is cosec x over 2. So they're not identical. Okay. Similar shape, but vertically, they're stressed or shrunk, they're not same. Next, particularly the range will not be the same. Okay. The line x equals 0 is a vertical asymptote for y equals cosec 5x. The line x equals 0 again is a general knowledge here. X equals 0 is the equation of y-axis. Is y-axis an asymptote of cosec x? Yes, right? At 0, cosec sine 0 is 0, so cosec 0 is undefined. So the y-axis is an asymptote. Okay, as we saw here, this. Now the y-axis is an asymptote. But what about 5x? Doesn't matter, right? If cosec 0, if x is 0, then 5x is also 0. So that y-axis would still be an asymptote here. So the answer here is okay. Some more practice problems now. Sketch one cycle of the function 2 sec pi x over 3. And we will, try to obtain these parameters first, domain range and stuff like that. Here multiplying by 2. We've done this work before. Okay. So multiplying the angle does not change the domain. Sorry, range. But multiplying by 2 changes the range. And that's easier. First, let's do that. Negative infinity to negative 2 now. Okay. Because your values are, vertically stretched. So instead of negative 1, now the values will be negative 2. And similarly, on the upper side, you will be only from 2 to infinity. That's the range. What about the domain? The domain will be affected by the action that is being done on x. And our technique is very simple. The argument for the function sec, the argument, the input to sec should satisfy the condition for sec x that we studied. It should not be a multiple of odd multiple of pi over 2. So not equal to 2n plus 1 pi over 2. Then you solve for it, simplify it. Okay. Luckily, this is easy because you don't have to add or subtract. You take that pi over 3 and flip it on the right side and multiply, right? The rules of algebra dictate that. And the pi will get cancelled. You will get 3 over 2 times 2n plus 1. Okay, when you simplify that, it becomes 3n plus 3 over 2. Okay, and um, so how does it matter? It's 3n. It's a multiples of 3 plus 1.5. Some strange values of x. Okay, that x cannot be actually x not equal to. Okay, so that implies you can write like this: x is not equal to that. So the values of x that are not allowed in the domain is multiples of 3 plus 1.5. So that would be something like 4.5 or 7.5 or 10.5 and so on. Okay, and I will formalize that here by writing it in the domain. So x says that x is not equal to 3n plus 1.5. Okay, and okay, if you write 1.5 like that, it looks confusing. So let me write 3 over 2. What about the period? The period of the function will be again affected by that pi over 3, and the answer is simple: 2 pi over pi over 3. Okay, the coefficient of x is pi over 3, and that becomes 6. Period is 6, and the asymptotes will be exactly those values. Equation should be x equals 3n plus 3 over. Okay, and you can now draw the graph based on this information. Do it yourself and then check with me. One cycle. Okay, you have to sketch only one cycle of that. While you are doing it, um, I will show you the answer directly. While you are doing it, just bear in mind this time your the partitions on x-axis, the markers on x-axis are not multiples of pi, but they will be in terms of integers only, because your period is 6. It's an integer. Okay, and that's always the case when your angle itself is multiplied by pi. you know the input is pi x over 3, so the pi there takes care of those multiples of pi on the horizontal axis. Okay, so instead of that, you just take integers now: 1 2 3, -1, -2, -3 as markers on the x-axis. Okay, so here is some of the work, which if you have already graphed it, you will be able to follow, or else it will help you. I highlighted a small green table on the right side of the graph, top right, where I have calculated the x and y values. I mean the input and outputs for a number of input values. Okay, which is, if you plug in x equal to 0, for example, okay, 2 sec 0, and sec 0 is a reciprocal of cos 0, so it's 1, 2 times 1, 2. And similarly, on the top of this page, you can see I have calculated for x equals 1. Sec, sorry, we're evaluating sec pi over 3, not cos. Okay, I need to change that. Sec pi over 3. I was thinking it's a reciprocal of cos pi over 3. Okay, cos pi over 3 is half. So the sec pi over 3 will be 2. 2 times 2, 4. Okay. So similarly, you can calculate at 2 and 3 like that, and you get those values on the right side. And then you realize cosine is an even function. Recall that? Okay. So its reciprocal also will be even function, which, if you have forgotten, I will write here. The definition is f of negative x equals f of x, an even function. Okay. So the same output values will occur for negative values of x. So plus minus 1, plus minus 2, plus minus 3, the y values will be the same. Okay, corresponding y values will be same. So that helps you to now mark those points. And then I also looked at asymptotes. Okay, and our formula was that asymptotes occur at 3n plus 3 over 2, right? So you choose some small values of n. I took 1 first, I got 4.5, but that 4.5 is beyond our graph here. Then I took -1 and I found -1.5, which is on the left side. You can see the asymptote. Those dotted lines will be the asymptotes. And then I was wondering, I should have two asymptotes in one cycle of this graph, right? Because we have graphed the original fundamental period earlier, and I remember there were two asymptotes in that. It took a while. I realized I can also use n equal to 0, right? N is an integer. So when you plug in n equal to 0, you get x equals 3 over 2, which is 1.5. So you have these two asymptotes in this period from -3 to 3, by the way. The question, the length of the period was 6, right? So I had to choose a cycle, and the x-axis and y-axis in the graph were already marked. So I thought, why not go from -3 to 3? That will be one period of this function. And then I looked at I found the asymptotes. Then I calculated the table, and in that table, the values that I have at 0, it is 2. So 0, 2, 1, 4, those are the points I have plotted here. I'm going to show here like 0, 2, that's here. 1, 4 is here. Then because it's an even function, at -1 also you will have the same thing, -1, 4 here. Okay. And at 2, it is -4 down here. So at -2 also it will be -4. At 3, it is -2. So at -3, it is -2. And then I could predict the pattern. Okay. I did not calculate. I just predicted that at 4, it will be down here, -4 here. And now you are seeing what the shape of the function should look like. And one more intuition you should keep in mind here is the fundamental, the view of the graph is going to be the same as the graph of sec x. This is only a transformation, it might scale it up, it might move it up, down, left, right, but you don't change the fundamental behavior of the graph, fundamental outlook of the graph, right? And that you can see here from these points, and how you should draw a curve which fits in with those being the asymptotes. Okay, and we can do that together now because that's a minor work remaining now. So it will be asymptotic there and down here, turn back from here and go up and being asymptotic there. That will be one part. And if I go to the right side now, it will be asymptotic there, then gradually go down and move up. Maybe a little bit more smooth than that, not exactly like a parabola. Okay, let me redo that. More like a U shape, And then again, gradually I'm being asymptotic at 4.5 after that. And similarly on the left side, asymptotic to -4.5 here, down, up, and again asymptotic to in the left here. Okay, that would be one cycle of that function. Okay, here's another question. Find the equations of the vertical asymptotes of that function. Okay, I'm glad that we've got enough practice by now. So you know what to avoid, right? That pi x plus pi, the argument to the secant, should be not equal to 2n plus 1 pi over Okay, and then you have to solve for it and factor pi out of the left hand side. You get x plus 1 not equal to 2n plus 1 pi over 2. And then now you can find pi on both sides of the equation. You can cancel it out. What remains is x plus 1. Take the 1 to the right side and subtract. So x is not equal to 2n plus 1 times 1 over 2. Pi has been cancelled. Okay, minus 1. And I'm going to simplify that now. That will be n plus half minus half. So it will be n minus half. So n plus half minus 1. So that will be n minus half. You can actually see if you take common denominator, it will be 2n minus 1 times half again. Anyways, so looks like after all it remained as odd numbers. Okay, odd multiples of half now. Odd multiples of half would be like half, 3 divided by 2, 5 divided by 2, and so on. Okay, so that will be like 0 0.5, 1.5, 2.5, and so on. And whatever this 2n minus 1 is still an odd number. Okay, general expression for an odd number could be 2n plus 1 or 2n minus 1. Both of them will be odd. And because we are going to take all possible values of n, integer values of n, so it doesn't matter whether it is 2n plus 1 or 2n minus 1. You end up getting all multiples. Okay, all odd multiples. Here I should mention at the end, n is any integer. That would make the answer complete. Okay, those will be the, what am I saying? Those will be the equations of the vertical asymptote. And I made a mistake here. All of these should be equations. If you are talking about domain, you will say not equal to. If you are writing the asymptotes, the same thing you say equal to. Okay, sorry about that. Just replace everything with equation. Okay. Write the equation of the vertical asymptotes. Now, you get to practice. Please do it and check with me. I'll run through this a little faster. Here, 2x minus pi should not be equal to multiples of pi, integer multiples of pi. Sorry, equal to integer multiples of pi. And now that gives you 2x equals n pi plus pi. So x will be, I'll do both the things at the same time. Okay, I'll factor out pi and also divide by 2 on both sides. So you get n plus 1 pi over 2, which is after all multiples of pi. When you take all values of n, it doesn't matter you say when n plus 1 pi over 2 or n pi over 2. Okay, so the simple answer would be all multiples of pi over 2. You can, as an answer, you can leave it here. Okay, but in your mind, you know it doesn't matter. You could have just said n pi over 2. It matters if you are looking at a finite range, okay, where the values of n will exactly tell you which pi over 2's are you including. But in the infinite case, n plus 1 times pi over 2 or n times pi over 2 are the same. Think about that. Okay, we did that for secant. Now repeat a similar exercise for cosecant here. Okay, I will pause the video, finish this and show you. You also do the same and check with me. Okay. You can see some of the work I have done here and cross check that with your own work. I have not yet graphed, but I'm almost there. Okay. I wanted to discuss the progress so far with you. So first you can see in purple color, I calculated the domain, and turns out domain cannot be the values of x, everything except the values of x, where they are n minus 1 times pi over 3. Okay, but like my previous discussion, that basically means n pi over 3. Okay, so any multiple of pi over 3 cannot be in the domain. That means that is where you will have your asymptotes as well. So the domain and asymptotes is taken care. The range will be the same as original cosecant function because you are not multiplying the cosecant in its coefficient, only the angle is input is changed. So no stretching here, the same domain, and the x is multiplied by 3, right? So the period gets shrunk horizontally. So 2 pi over 3 will be your new period. Okay. Then I was thinking how to show one cycle in the graph. The period is 2 pi over 3. Okay. So in this grid, we are going to go from minus pi over 3 to pi over 3. You choose your scale, because so that means this whole graph will show you one cycle. And then you can strategically evaluate some of the values of the function, right? So if the 4 units are like pi over 3, then at halfway mark you have pi over 6 and negative pi over 6. And then on the top right, I evaluated the values of the function at these marked points. Okay. And you can do that by plugging in the value of x in the equation. If you plug in 0, you get cosec 0 plus pi. So basically cosec pi, and that I remember is reciprocal of sine pi. Sine pi is 0. So cosec pi is undefined, plus minus infinity. But when you plug in x equals pi over 6, you get 3 times pi over 6 will be pi over 2. So cosec pi over 2 plus pi is cosec 3 pi over 2. That's 270 degree, 0 minus 1, where the y and the sine of the x is minus 1. Cosec x is reciprocal, so it will also be minus 1. So at pi over 6, I evaluated that it is minus 1. Then I remembered cosec x is an odd function. Okay. And I'm going to write that here now. You should also make note of it. It's a reciprocal of sine function, right? Sine is an odd function, so this is also an odd function, which means I don't have to calculate again. At negative pi over 6, the y value will be 1. The characteristic of odd function is, I'm going to write above there. If you evaluate the function at a negative value of x, you end up getting the negative value of your original value. So it will be negative f of x. Okay. And that's the logic we used here. Then similarly, again at pi over 3, it becomes undefined. So I was thinking, we have this data now. Okay. Why did I calculate the pi over 2, 12? I will show you that now. So we have this idea here, okay, that the asymptotes are at 0. You can see here, okay. Even from the table of values, you can see here you have asymptote at 0 and at pi over 3. We had said that, asymptotes are multiples of pi over 3 here, okay. So I have an asymptote here at 0, that is on the y-axis, and then again an asymptote at the end. here. Okay. And similarly, there will be now an asymptote at the left end also over here. And at pi over 6, the value is -1. So here, at pi over 6, the value is -1. Okay. So I think I have an idea, what the graph should look like, because the values are not going to cross the x-axis. They don't take values between -1 and 1. Okay. And similarly, at negative pi over 6, the value is 1. So I know now it's going to be on the right side, it will be, upside down, and on the left side, it would be facing up, right? But wanted to be more clear about that. So I evaluated the value of the function at pi over 12, because I know pi over 12 will be like halfway between 0 and pi over 6. So that, on the grid there, and I will show you the evaluation at pi over 12. I wanted to show that evaluation also, so I did that. You go to the original function cosec 3x, right? And you are plugging pi over 12 for x plus pi. Now that 3 and 12 cancels and you get pi over 4 plus pi. So now, where is that angle? Pi over 4 plus pi. Pi is 180 degree, negative x-axis, plus pi over 4. So you are in the third quadrant. In the third quadrant, y coordinate is negative. So this will be the negative cosec of pi over 4, okay, which is the reciprocal of sine pi over 4, and that value is root 2, and hence you get the value negative root 2. And that, if I am able to sketch it, gives me more confidence, So it will be negative root 2, which is negative 1.4142, somewhere here. Okay. So which confirms that it will be the U shape facing downward in that strip of between two asymptotes, facing upwards on this strip. Now you know how the graph looks like. If you have not already completed, please go ahead and sketch it. That is how it should look. Okay. All right. Moving on. Write an equation. We have three more questions and these are simple ones. Okay. We're almost done. Write an equation for the graph of y equals sec x shifted. We are going to go through these transformations and write the final equation. Shifted pi units to the left, then reflected on x-axis, and then shifted 2 units upwards. Okay. Let us start writing from the beginning and we will see what updates need to be made. Pi units to the left, that is horizontal shift. Maybe I want to keep some gap or coefficient if needed, we will see. If you shift to the left, you are adding pi to the phase shift, plus pi. And then you reflect on x-axis, so the positive y values become negative and vice versa. That is obtained by putting a negative sign to the whole function. And then you shift it 2 units upwards, which is simply plus 2 at the end. Okay. Next, you can write your answer and check always. Okay. Write an equation for the graph of y equals cosec x shifted 2 units to the right. Okay, I'm going to start right away there. Cosec x shifted 2 units to the right, reflected on y-axis. Okay, now when you reflect on y-axis, you're evaluating f of negative x. Okay, so I have to do this. I have to erase the cosec here. I'm going to move it a little bit more to the left, put a second set of parentheses and apply the minus sign here. That is reflection on y-axis. Okay, the x becomes negative x, and then shifted 1 unit downward. Separately you will do minus 1. Okay, you want to simplify it, write it in a neater way. You can write cosec negative x plus 2, or 2 minus x, we will, minus 1. The vertical asymptotes of cosec x, the last question, the vertical asymptotes of cosec x pass through the, okay, this is conceptual, okay. Where will you get vertical asymptote for cosec x? Where the denominator in the ratio is 0, right? Where, that means that is where the sine x, because sine x is the reciprocal, should be equal to 0. So those are the zeros of sine x. Okay. Similarly, the vertical asymptotes of, what's the other example? Sec x pass through the zeros of cos x. Okay, so this is one beautiful connection to remember. The vertical asymptotes of these reciprocal functions are where you have zeros of the original function. Okay, thank you for watching. In the next video, we will talk about graphs of tangent and cotangent.